So we can all stand, or we can. I'm just going to hang out over here.
All right, all right. Hey, welcome everybody. Thanks for coming. My name's Chris Malone. I'm with Meta. I'm responsible for data center technology strategy. I work really closely with groups across Meta, hardware, network, software on co-design of our data centers and hardware and so on. And today I'm going to kick off this session with a very brief, as brief as I can be, intro to some of the work that we've been doing as a group. I'm not going to introduce my panelists in the interest of time. They're going to do it themselves when we flip to that part of the discussion. But to that point, here's the companies that we've been partnering with and aligning on the topic of temperature as it relates to liquid cooling. And so we have ourselves, Meta, Microsoft, AMD, Samsung, Intel, nVidia, and Equinix. And so just to give you some grounding on this, we all know that liquid cooling is coming into the mainstream. I walked the exhibit floor today, and there's just like a lot more real things out there. And with the emergence of AI, that's really driving this change. And when a few years ago at Meta, we were looking at designing a AI-first data center, sort of anticipating this demand. And one of the open topics was, what temperature do you pick for your liquid? And if you go at that time, looked around the industry, there really wasn't any consensus. There were kind of an effort around super low temperatures, below 20 C, what have you, to future-proof against all potential outcomes, which is expensive from a CapEx and OpEx perspective. And then there was interest at the higher temperature, 50 C kind of temperatures, which enables great efficiency, which we all love. But what we found, kind of looking hard at the AI futures, where our chips were going, that neither end of the spectrum was great. So 50 was too high, 20 was going to sacrifice all of our efficiency, but 30 was about the right spot. It also aligns with what we use for our air-cooled devices, which are going to continue for the foreseeable future, probably for a very, very long time. And a lot of hyperscalers already operate at that temperature. So 30 allows for a reasonable amount of future proofing, and then we'll talk about that with the panel, and also I'll just kind of hint at it a little bit here. And so, that's really the basis for the work we've all done as a group. And so what's great today is we have a whole bunch of industry folks that are kind of working together with us on this. I introduced the topic back at OCP 2 years ago, and we had another meeting earlier this year at the regional summit, and this represents kind of the next iteration where we've pulled a lot more folks in. And so one of the key things here is, we're saying 30C, we're working with ASHRAE and other groups to sort of align around this, but we know it's not name a temperature and you're done. It's actually very tricky. We know that AI chip power is going to increase over time. The complexity of the chips are going to increase, et cetera. So we need to invest in chip packaging as an industry and the associated thermal technologies as well. So here's a couple charts. They're incredibly complicated. We could spend the entire session kind of talking about that. But just to give you a kind of a quick overview, this is material we presented in the spring, so it's all available out there to view. On the left-hand side is a chart showing power on the horizontal, and on the left axis, it's years, so release date. And those two, the red line and the green line, the thickness represents uncertainty. The red one is your traditional CPU. So we see power going up, that's no surprise. The really important point is the green one. That's the AI module power that's going way up and very quickly. We see like 1,000+ watt chips happening in the not too distant future. And on the right-hand side is a projection looking at required liquid temperature. So this is a cold plate kind of centered analysis, but it shows you're asymptoting out at around 30 C to kind of protect against the future. So that's sort of the underpinnings of the analysis that supports this work. On the right-hand side, is kind of articulating one of the major challenges with the AI modules, and that is HBM memory or high bandwidth memory. With these chips, it's important to put as much high-speed memory as close to the ASIC as possible. So we do that with HBMs, which are basically stacked silicon. And over time, we want more and more and more. So this chart basically says we're going to move from, from 8 to 12 to 16, and it's intuitive that that cooling problem is going to get harder. So this is just a kind of a very quick review of some of the trends that we see happening over time. And so just to wrap this part up, like, why do we care about data center durability when we're thinking about these temperatures? As I already kind of hinted, we don't want to backtrack on all the efficiency gains we've made as an industry over the last 15 years, and that 30C kind of allows for that. If you lower that temperature, it has an immediate impact on efficiency. And then the other thing is data centers are capital intensive. We expect well in excess of $200 billion to be spent globally on the industry. And more importantly, they take forever to build. So you make a bet, they're fairly inflexible resources. So you want to make sure that you're investing at the right operating point. So with that, I'm going to conclude and we'll move to the panel session. And here's some links to some of the presentations we've already given. All right, thank you.
All right, thanks for that, Chris. Why don't you guys spread out just a little bit? We'll use the whole stage for the panel. Let's go one more. Let's move this slide one more forward so people can see who all is talking. All right. So to start the panel off, we're going to talk to you, Shri, first. You're up first. So this group has been working together since 2021. So can you tell us what all has changed?
Well, thanks. Yeah, the liquid cooling part and the it's been going on for 5 years, and we are trying to have cross-functional or across the industry have a sync for since 2021. But with the advent of AI and the power and what we have just seen here, it's high time that we kind of look at it from a collectively as an industry, how we want to do and how we really want to be effective. So.
Yeah, I mean, one of the other things is, too, you mentioned 2021. Mm-hmm. I don't know about all of you, but in the last year, just seeing the explosion and sort of the arms race, I keep hearing that term, right? One of the most amazing things to me is to think about ChatGPT came out in November of last year. So as of this conference, it's not even a year old yet. So when we talk about what's changed.
Yep, that's definitely a big one. Okay, so Chris, this next question is for you. Right. So why is it important to drive alignment between hyperscalers, data center operators, and component suppliers?
Right. Well, I kind of hinted at some of this in the opener. These data centers are inflexible. They're long-term bets. These things are meant to operate for 15 plus years. And so we want to make sensible bets in terms of the designs so we don't over provision, which historically data centers have done at the expense of efficiency. The other thing is, it reminds me of some of the dilemmas we had in the early 2000s around air cooling, where there was no standard, and ASHRAE really helped out in kind of narrowing the gap, like kind of clearly defining the operating points for these systems. Yeah, because the individual server vendors were coming up with their own specs, and yet everything was landing in the same data center. So it's kind of absurd that these companies were competing or delivering mixed messages. So it's not the same thing here at this stage, but there's analogs, right? So efficiency matters a lot more now because the scale is dramatically larger. So every megawatt counts, right? So in terms of your waste. But fundamentally, the similarities are we're all using the same basic components. We all have, at the data center level, there's a lot of commonality in terms of what's available. And then with the chips, like there's also some pretty common solutions for how to manage power, how to package. And so moving that ahead is going to benefit us all. So that's kind of one thought on that.
Yeah, I was going to add on to it from my side, from the silicon side, it's very useful. Again, ASHRAE kind of set that bar. So internally, what happens is marketing is always coming back and say, but I want 27, or I got a customer who wants 25, or I can get another 10% performance. So having that bar that's consistent that we're all agreeing on really makes our jobs easier to kind of close those holes. And same with ASHRAE, when we're doing A2. That's what it is. It's 35C. So it's very helpful internally also.
Yeah,
Plus
I think like it's basically system co-design, right? So my philosophy with co-design is all the partners should be a little bit unhappy, right? So we don't want the chip guys to get off the hook and design with this wide open band of temperatures.
And Chris, I'll add on to that. As a co-location provider, like it's really important for us to drive a consistent standard across the board. As you were saying, Paul, like we have asks all over the place for W10, W12, W15, and having like a very clean floor where we set a consistent temperature across the board while still delivering the performance that we need across the ecosystem is really important to us. So we really want to support that.
Yeah, and I'll add on too, also from the silicon side, that it helps us a lot in terms of setting expectations internally about what we can support, what power levels we can support, knowing what's possible for different customers. And 30C as the floor is really important. It's also worth noting that there's still some places like Europe and others that do want higher temperatures, and so it's a floor. It doesn't mean that for those that are in Europe that are running at higher temperatures that, too bad you can't take, no chips for you. That's not how it is. Like there'll still be a market, they'll still be able to run the processors. There's just a different level of power that can be enabled.
Yeah, just on that point, like I think most hyperscalers, most data center providers have this flexibility to operate at higher temperatures, and we take advantage of that when the situation permits it. Right? And that just means you take an asset like a data center that can achieve some low temp, but we float the temperature up or use less power in the fans or whatever, like to adjust to what's actually needed. We're not going to operate at the lowest possible temperature all the time just because.
All right, that's great. That's great. So, David, this next question's for you. So, what particular technologies is this recommendation for? I mean, are you looking for cold plates, immersion? What is this?
Yeah, so I think it's worth clarifying, especially on the back of a morning focused on immersion, that this is very focused on direct-to-chip liquid cooling, primarily for single-phase direct-to-chip liquid cooling, really looking at primarily PG25-based solutions. Of course, treated water is going to be incrementally better. Yeah. But that's really the scope of the technologies that this is applicable to.
And at the same time, while that's a focus, we definitely don't want to exclude any technologies. When we say it's a temperature at the chip, it doesn't really preclude anybody from using immersion direct-to-chip or anything else that might come along that we're not thinking about. So,
Right.
All right, so following on that, Kelsey, so why is 30C kind of the preferred temperature and not something else?
Yeah, and I think this is really the crux of the talk. We've kind of gotten this question a lot. As Chris kind of kicked it off, I think it's really a balancing point. So I kind of think about four things. Certainly, we want to drive the temperature higher at the data center because we're looking for efficiency. Higher temperatures usually mean we don't spend as much energy. The chips, I think, are generally trending lower. And while the silicon providers may want to provide or allow higher temperatures, I think we can see the general direction it's going as we saw that chart. And one of the things we've talked about too is like just because your car redlines at a certain RPM doesn't mean you'd want to drive it that way all the time. So we want to even try to provide a little bit of margin there. The third, we also said we want to provide for some traditional air cooling hardware. So if we have facility water in a data center, we may still need to run AHUs and provide for air cooling hardware that we may also put into the data center. And kind of the fourth thing is just the longevity of the data center, right? So we talk about these data centers being 15-year assets. I was just talking with somebody yesterday about, think about 10 years ago when a 5 megawatt data center deployment was considered huge, right? How many of you can raise your hand and say you know what it's going to be in 15 years, right? So we're trying to provide a little bit of margin on top of that, right? So those four things, you try to balance all of those things together, and I think that's where this panel has really come and said, 30 degrees feels like the right balancing point.
Yeah, I was going to kind of add to that Chris mentioned it too. I think there's a little bit of unhappiness on all sides, right? It's not a perfect solution. So from a silicon perspective, it means I've got to do a lot of improvements in my packaging. I can't just go iterate what I have now and get there. And it's not low-hanging fruit. It's a lot of small things I got to marginally improve. And sure, I'd love to do W40, and that's what's doing, 40-degree water in Europe. but we just don't see a path at these powers. It doesn't mean you can't do it at different, if you're talking compute, it's a lot easier. But when we're talking about 1,500 watt GPUs, Forrest from AMD said 1,600 watts, right? So it's, again, it's kind of this arms race on performance.
Okay, so Paul, since we're talking about 30C, right, there's lots of different loops inside the data center, in particular in different temperature set points. So what specifically are we talking about here when we
Yeah, and this
30C?
does get very confusing. So it's the water directly to the server. So we're calling tactical fluid, it's secondary fluid, it's also what it's called from the CDU, but we're talking the fluid that goes directly to the chip. So it's entering the server is the fluid temperature we're talking about.
Okay. So Mai, this question's for you. What are the implications as a data center operator for going below 30C?
How about we start with an implication if we go up above that?
All right, sure.
Again, like left unfettered, like data center operators should probably let you float up into the 55 C without any issue, and we'd let you operate happily there. But the reality of the balance point here is the more that we drive that temperature down, the more energy we spend inside of a data center, really on cooling and getting that chiller plant running and driving that water temperature down on behalf of the performance. So it's really a critical balance for us to make sure that we provide the best amount of efficiency in the data center in conjunction with the best efficiency from the compute side of the house. So it's a really interesting balance point for us, again, to make sure that everybody's like equally unhappy. 30 degrees C feels like the equally unhappy point. We're equally unhappy to drive into that W27 range from that technical fluid loop, but allow for the performance to still exist there.
Yeah, and I think it's we've been talking about water for so long, and then now we're transitioning, and you always said water's 100 times better, it's so much better. And I think people are like, well, I'm going to do 60 and 70. And I'm going to be able to do warm water. And no, I mean, there still are limits that we're going to. Our powers are 3, 4, 5x what we were talking about before. So yeah, it's better heat transfer. But there's still limits on how much flow we can do. So I think there was a perception of liquid's going to save everything, and we've been selling it really well as an industry. But you're just hitting in different limits, and you're hitting them quicker.
Yeah, I think getting some of the facts out there about what the limitations are is one of the key things that we're getting to with this group, and there's going to be ongoing work to get more specific about it. But yeah, we've already talked about it a bit. Data centers pick a design point, they spend billions of dollars, build it out, and if you change your mind and you want to go lower, it generally means time and money, downtime, et cetera, to fix it, or at the very least, as I also said, we backtrack against all those efficiency gains that we've captured over the last 15 years. I mean, the old school data centers, which still exist, are freezing cold. And why? We've been on this journey to kind of get better with that total system efficiency. And so that's, we want to keep that going.
I think I'll jump in here because on the silicon slide, we do care deeply about the end-to-end energy efficiency. It's like we don't just stop looking at power when it leaves our chip. It's like we care deeply about how that power is consumed, like how much extra power is consumed, amortized across the silicon as it goes through the stack into fan power, into the data center power consumption, all the way until the heat is ultimately discharged to the thermal ground, which is the ambient environment. And so within that, there's a lot of concerns then about, it's worth noting the flaws in PUE, actually. If I've given a soapbox, I have to say that, because it abstracts the fan power consumption, which is meaningful for an air-cooled system. We get rid of a lot of that going to liquid, which makes it very attractive from an environmental standpoint. That's just really worth highlighting here.
I'll stack on top of the releasing to ambient. I think there's a lot of interesting regulatory environment occurring right now that really requires us to think about heat reuse. And so like this higher temperature also allows us to really consider that heat reuse story a little bit more carefully.
Okay, so let's kind of keep talking about that. So David, this is for you. So what do you see as kind of the risks from a chip design standpoint with setting a 30C target?
Well, one thing I'll note here is that we've moved beyond the phase where the computer is just a 1U or 2U server, in that if you look at ChatGPT, it's like ChatGPT was trained on hundreds and thousands of GPUs, right? And so the entire data center is a single computer, and so then as you look at that, the single computer running effectively a single job over many different nodes, that power consumption, there's a lot of power that's spent in things like networking and other things, and so there's a drive to increase power density by putting those computing elements, the GPUs, closer together, reducing transmission losses, just in terms of the data communication between the systems. And you follow that trend down from these large nodes, putting them closer together, saving on power from the signaling, and then you take that down even further to within the node of getting the chips closer together, CPUs more tightly coupled to the GPU for, again, more energy savings there, and then you drive that down deeper into the silicon itself, getting memory closer to the GPU. You just see this trend towards higher power density all the way down because of, and so that looks like the chips are going up in power, which it's true that they are, but you're getting a lot more performance as a result because you're concentrating that power into the place where the work is most meaningfully being done. And so it's power being consumed, but not all power is equal. It's like back to the PUE thing. It's like fan power is not the same as power consumed on the chip, right? But the PUE metric, it looks the same, but higher power density on the chip really delivers a lot more work. And so enabling that higher power density within the system and within the chip is really where this helps.
So Kelsey, you want to talk a little bit more about like PUE and WE, kind of the data center level?
Yeah, so I mean, this is something that I've talked a lot about, especially because as the industry moves now, I mean, you go back a little bit, we certainly, when we're talking about PUE, it was becoming a huge thing for our industry, and so we moved a lot toward water use and free air cooling, evap, and so forth. And now I think we're seeing a lot more communities kind of say, hey, water use is a really important thing. We really need to pay attention to that, and so we're seeing this shift. And then how do those two relate? It's maybe a little bit difficult to figure out like how a million gallons of water relates to however many kilowatts in terms of PUE. And then, as David has pointed out, when you have a lot of fan power in your servers and so forth, we just kind of brush that under the rug of the PUE number because it's all in the IT power. So as we move toward liquid cooling and we're taking some of that fan power out, put it toward pump power, I'm kind of, maybe a little bit concerned about how the industry is viewing, PUE metrics and these kinds of things, and really developing the apples to apples comparisons.
So as one of the originators of PUE way back, it was an attempt to move the industry forward. That's absolutely true that now that we're commingling, the cooling with the hardware, it gets much more complicated, which is actually amazing to see. It has a lot of upside benefits to it. But yeah. Agree.
Paul, I've got a question for you. So can you talk a little bit about how this initiative aligns with the work that's getting done in ASHRAE for us?
Yeah, sure. So, Chris said 2 years we kicked this off. He kind of presented at OCP. We were in the process of updating the TC 9.9 handbook. So I've been in ASHRAE for about 20 years. So it kind of dovetailed. We wanted to make sure that they're aligned. So we are doing S30, so 30-degree temperature is our lowest set point. We go up to all the way to 50 on the high side, but we're defining that explicit temperature into the compute because prior we defined the water temperature for the facility, which is not the temperature that goes into the hardware. So we had to have that. So we are aligned and driving a similar message. OCP's got faster throughput, which I love. And then you kind of catch up with ASHRAE and document, and it's a different audience that consumes that versus OCP.
Okay. Yeah, it's good that they're all heading in the same direction though. Chris, for you, so as we look to the future here, what do you see kind of as valuable next steps for this particular group?
Yeah, first I'm super delighted at the progress we've made. We have a really rich conversation that led up to this presentation, as we do with all of them, and great progress. I think we have published some work in this area. We need to get deeper into what are the chip level issues. How does chip packaging help us move forward? Same thing on the cooling side. Like what innovations in terms of directed chip cooling do we need to work on as an industry? And as I said earlier, these are common problems. So it's better for us, through OCP to sort of share like what the common problems are so we can enable solutions at scale. Because it is really difficult, especially for hyperscalers and large-scale colo providers, to bet on niche technologies when you have to build out them at gigawatt scale. So more development of common solutions and understanding the fundamental technical hurdles is a really important thing.
Yeah, and I would add on that too that memory just gets really interesting. So traditionally, if you looked at FPDIMMs a while ago, that was really hard to cool. It was 18 watts. It had an advanced memory buffer. And then memory was easy. Memory's been really easy to cool. Now you start talking about MRDIMM, MCRDIMM, Monument Creek from Intel. You talk about HBM, you talk about 8 stacks, hundreds of watts of power. I mean, and it's not optimized for cooling. When you do a lot of chip and you're designing that for that cooling environment. So I think there's some opportunities there that are not that obvious that are things we'll have to go look at.
Okay, great. So we just have a couple of minutes left. So if there's anybody out in the audience who'd like to ask the panel a question, feel free to step up to the mic.
So you're talking about the approach temperature to the chip, but what do you see as the temperature the actual data center will operate at, and what would be the ideal delta T in your mind to actually run that?
3 to 5, right? I mean, you would in general, we a 3-degree approach temperature between primary and secondary is kind of aggressive. But 3 to 5 kind of range, you would look at it, and it depends on your water source too. Maybe you're in Switzerland and you're taking off the bottom lake, so you don't need a low temperature. But aggressive is probably 3 degrees.
Yeah, I think that one of the things we did think about is like getting into the delta T specs. I think there's a bunch of different ways you can develop cooling plants that have cost and efficiency hits associated with them. So there's some level of autonomy in terms of how you manage that side of it. But like what is clear is we need to understand the temperature in close proximity to the chip. Like that is the key thing.
Yeah. And I think it's worth noting here that if you talk to the different CDU manufacturers, both liquid-to-liquid, liquid-to-air solutions, there's not a lot of commonality in terms of when they spec X kilowatts or X megawatts of capacity for a CDU. You always have to ask what the approach temperature is because there's not always consistency there, and that of course makes a big difference on the cooling capacity.
All right, that's good. We're out of time. So thanks, panel. That was great. Appreciate it.